To discuss contest 15. Contest 15 was harder than expected. Two last problems. So first 6 problems are okay. Actually, problem H is okay. Problem G is too hard. That's actually happening too often lately. So I don't know why. So I usually pick problems at random, and I only look at the difficulty. So I read the problem statements, but I try not to think about them that much, so I don't spoil myself all the solutions. So I read the problem statement. That was some game difficulty. Okay, difficulty of this problem is actually, let's see, I think it's something about 2000. So it's not that extremely difficult problem supposed to be. Okay, code forces is not working. Okay. It's actually pretty bad code force not working because I don't have problem statements. So let's save them somewhere just in case. Okay, sorry. More reclamations. Code forces. Okay, it's so slow. So slow. Okay, okay. Google says it's okay. 2100. Okay, so it's not extremely difficult, but it turns out to be, again, maybe I'm doing something wrong. I spent like an hour solving problem H. Okay, you can see here. 33. Yes, because I spent 1 hour solving problem G, and then okay, why it's not updated? And then another 50. Okay, how much? Like 15 minutes solving problem H. So problem H surprisingly easier for me than problem G. Maybe just me, I don't know. My solution is extremely hard for some reason. So everybody who solved first 6 problem, good for you, very good result. Okay. Let's go. So let's discuss all the tasks. Again, I started recording myself, but I stopped the problem G. We can watch the first recording, but it's not very fun. Again, I will not show you all this 1 hour struggle on problem G. It's not very informative. So let's just discuss problems one by one. Problem A. So we start with very simple problem this time. So it is simple but still interesting. So we have zeros and ones. We can remove 0 and 1, and we need to remove as many digits as possible. Yeah, and it says we can only remove 2 adjacent positions, but if you think about it, it doesn't matter. Yeah, if you have both zeros and ones, then at some point you must have 2 adjacent 0 and 1. Yeah, so it doesn't matter. So you remove 0 and 1, and so the only numbers you left are the numbers which don't have pairs. Yeah, and you calculate how many zeros you have, how many ones you have, and the difference of these numbers basically the result. I just calculated like this. So I calculate difference between number of zeros and number of ones, and output the model of this difference. Yeah. So that's my pretty simple solution, I would say. So this time first problem is not difficult. So finally, at least this. Okay. So again, I would say first 6 problems are not that difficult. So this is the first one. Okay, nothing much to discuss here actually. Nice easy problem. Good for starter code. Did anybody have any problems? Okay, well, everybody solved it first try. Good for you. Okay, no corner cases, no special tricks. Just nice problem. Second problem. Okay, second problem is fun. So what we need to do? We have 2 digits, and we need to. So we have number from 0 to 99, but we also have exactly 2 digits. And we need to find other numbers which can be shown if we miss one of these lines. So let's indicators, how to call them. Sticks. Okay. So if you remove some sticks, if some sticks are broken, which other number can it be? Okay, and no, you multiple ways to do it. You can just check all possible 100 numbers, and for each number check if you can do it or not. To check if you can do it, you need to draw one number, another number, check if this number is the superset of this number. Yeah. Something like this. I did it like this. So I just manually calculated for each digits how many other digits can be represented like this. So how many other digits are the superset of this digit? So how many, so set of these sticks is superset of set of these sticks. Yeah. And I just did it by hand. No, you need to do something by hand in this problem. Yeah. So you given this picture, you somehow need to transform this picture to code. Yeah. So you can transform it as like bit vector of 1 2 3 5 of 7 bits. Yeah. So you can transform every digit to 7 bits and then just calculate this array. Right, sorry. I thought it just it will take approximately the same time to calculate this array by hand just by looking at the digits. Yeah. And then I don't need to write the code which calculates the digits. So again, it's always balanced between amount of time you spend on paper and amount of time you spend programming. Yes. So here I decided it will be easier to calculate these numbers by hand than programming. Yes. So I get this array, and now I don't need to encode all these digits. Yes, I just take this array, calculate how many digits can be in the first position, how many digits can be in the second positions, multiply, and get the total result. So that's my solution for this problem. I believe there are very different approaches to this problem. I might actually mistake in the problem. So instead of this 4, I get 3 in the first my submit. Well, it happens. When you hard code some data from the problem statement, you may make a mistake. You just carefully check that all these numbers are correct. And if you have wrong answer, you check it again, like I did here. It happens. Not a big deal actually. So let's look what problems you had in this problem. So who's the first? Okay, you're the first. Okay, let's look at your solution first. Wrong answer test 10. No, okay, that's similar to mine. Yes, you have 2 4 3 3 4 5 1. Should be 7 somewhere. So some of them should be 7. So again, you missed one of these numbers. 2 7. This start looks strange. Okay, this should be not 4 but 7, right? It's pretty strange. Okay, you why I don't have the last number 9? Okay, have one from 1 to 8. No 0, no 9. Okay, so you didn't count all possible digits. It happens. What about you? Okay, also this is the same solution as mine. 11. Why you have 11? Why you have 11 here? I'm not sure. So if you have one digit number, you still have all the same things. So this part is really strange. So you always display 2 digits. So if the first digit is 0, you still need to do some stuff. So I believe 14 numbers. It's simple 55. Okay, so you miscounted also, yes. So for 5, yes, not 3, it's 4. Also same mistake as me. Okay. Okay, so you can do some silly mistakes in this problem, but eventually you solve this. Okay. Okay. If you didn't solve this problem, just try to solve it. Why didn't you solve it? It's a good problem to solve. It's easy problem. It's just some complications. You can do it. No special algorithm, no special tricks. Just careful implementation. That's it. So again, if you didn't solve these problems during the contest, I highly encourage you to solve them. It's very beneficial for you to solve the problems you didn't solve during the contest. Just do it slowly, take some time, solve them, or even after this discussion, you can go and solve them. It still be very beneficial for you if you write this code at least. Yes, just take your time and write this code. So next time you do it faster than okay. So that's problem B. Problem C. Problem C is really straightforward. I was actually, when I first read this problem, I thought we have some number theory thing with some n log n stuff happening. But then I found this 100 and I thought, okay, so it's actually just do, yes. So what we need to do, we just check all the frogs. We check all the frogs. For each frog, we have 100 frogs, yeah. For each frog, we count how many mosquitoes we will eat. It's just all numbers divisible by this jump. And just count them, find minimum. So that's it. So that's the whole problem. I don't know. So very strange problem. It's just very straightforward. Until you read this 100, you think it's some strange problem about divisibility and stuff. But this 100 kind of tells you write the most stupid code, and it just works. Again, let's read this stupid code. Okay, so what we have? So I read the data. So this part. So I need to find all the minimums. Yeah. So you need to find all the elements which gives you the minimal sum. Yeah. So the way I do it usually, I do it like this. So I remember the current minimum and the array of all elements which give me this minimum. Yeah. Now I scan all possible jumps. Yes. Count how many mosquitoes I will eat, just like this. Yeah. Then see if I need to update my minimum. If my minimum changes, yes, I update my minimum and clear this array. Yes. Okay. Now, if I have my minimum, then I push it to this array. Yeah. No, you can sometimes you can do it like this if you like it most. Or you can do it like this. You can up. I just say else, yeah, else, yeah, up, and here you push it like this. Also possible. So if you have new element is less than your current minimum, you just create an array of only this single element. Yeah. If it is the same as the previous minimum, you add your element to your arrays of minimums. Yeah. It basically does the same, but okay, up to you. So that's how I find it. Another way to do it is just to calculate minimum, and then in a second try you again scan all elements and find all equals to minimum. Yeah. So first you scan your array and find the minimum, and second time you scan your array and find all elements equal to this minimum. Also will work like in linear time, maybe a little bit slower, but doesn't matter. Fast enough, definitely. So that's it. So that's problem C. Why you didn't solve problem C? Tell me. What's the difficulty? So problem statement is a little bit overcomplicated. Yes, no, problem statement is long, but again, you need to learn how to read long problem statement. Sometimes they just long to scare you. So it's nothing interesting happens here actually. So you jumps and you eat all the mosquitoes which are divisible by your jump. Okay, examples not very descriptive here, but this problem set actually tells you everything you need to know. And this 100, yes. Okay, who had problems with this? So Alexis again had problems with this. What can go wrong in problem C? Tell me, Alexis. Wrong answer test 1. Really? Okay. So you're just lazy to test it locally. Like, what's this? Okay, stop doing it. Stop doing this. Okay, just make, okay, in another advice, just make good template and always use the same template. Don't use this crap. So why you don't have fast input here? What's this? So you will have problems always if you don't make it. Make some okay. So that's my template. That's something I'm used to. Yes. So it's not very not very canonical, I would say. Yeah. So but it's my template. I always use the same template. I know how it works. So I always have ints as 64 bits, I longs as 128 bits. I always have this part, so I don't need to include everything. I know how it works. I have simple. So if you always use the same template, you kind of know what to expect. Yes. If you use this crap, Don't be like Alexis. That's problem C. Okay. No questions. Okay. Let's do it. Okay, let's do it fast. We will spend a lot of time problem G, so I will go through first problems pretty fast. So problem D. I forgot problem D. Ah, okay. For problem D is actually fun. What happens in problem D? So we make jumps. So we start in position 0, yeah, and we make jump. First we make jump of plus minus 1. So every time we make jump to the right or to the left, then plus minus 2, then plus minus 3, and so on. And we need to make minimal number of jumps and get to position number x. Okay. So how to solve problems like this? No, you basically first just try to play with this system and see what's going on. Yeah. So you see, okay, where can I go? Yeah. So if you start in position 0, then you first make this jump. So you go to position -1 or to position 1. Not many options. Yeah. Then you have plus minus 2. No, where will you go? You go to 1. You can go to -1. Yeah. Then you go to -3, or you go to 3. Okay. Then you have plus minus 3. Okay. You can go to -6, -4, -2, 0. Okay, so 0 is not here. Here -2, 0. Yeah. Or you can go to the right. So from -3 you go to 0. From -1 you go to 2. And from 1 to 2 to 4. And here you go to 6. And from here you already kind of see the pattern. Yes. So you can visit every number with step 2. Yeah. Why you have step 2? No, because the parity is kind of fixed. Yeah. So plus and -1 have the same parity. Yeah. So if you add numbers with the same parity, you have the same parity in the end. Yeah. So all the possible results always have the same parity. They are even all even or all odd. Yeah. So all the numbers have the same parity. Now they always form the continuous segment. Now why is it true? No, because you have some segment, and then you move this segment some position to the left, or you move it some position to the right, or some position to the right. Yeah. And your length of your current segment is always greater than the step you do. Yeah. Because your steps grows linearly and length of the segments grows quadratically. Yeah. Okay. So again, you don't need to prove this actually during the contest. You just need to make these observations. Yes. So you play with this given model and see what's going on, and just observe some noticeable observations. Yes. Yeah. So you notice something interesting about what's happening. Yeah. And you think, okay, is it true or not? Yeah. And sometimes it's just true. So like in this case. So again, what you need to notice? You need to notice that you can visit all the numbers with the same parity in some segment. Yeah. So you always have some segment, and you can visit all the numbers with the same parity. Okay. That's actually enough to solve the problem. Okay, because it's very easy to calculate this segment. So the leftmost element is just -1, -2, -3, yeah? And the right number says 1 plus 2 plus 3. So every number between this and this can be visited if it has the same parity. Actually, another cool way to do it is just to check. So if you don't want to prove it, you can just check it. So you write this code. It's not that hard to write. Yes. So you write this code, run it, and just see if it works. Okay. Let's look at my solution. My solution is pretty simple. Okay. So that's the whole solution actually. So that's Problem is interesting, but solution is pretty short. So that's it, yeah. So I take the number, just calculate them. So I always have positive numbers for simplicity. And then I just do the steps until my segment contains element X and it has the good parity. Yeah. So while I have small segment or I have the wrong parity, I add more elements. Yeah. If I have enough segment and a good parity, I stop this while loop and output the result. Yeah. You don't even need some binary searches or stuff like this because, okay, this while loop works in time complexity like square root of x. Square root of x is small. Yeah, so you don't need even this. So you just normal brute force. Yeah, so what's actually happening here is the brute force. You also, I believe, can do it using binary search, but it's just overcomplicated. Okay. So that's it. That is problem D. Did you have any problems with problem D? Okay. Let's see. I actually also have wrong submission. I thought, let's see. I thought you can only do one more step. So I extend segment until it contains, and then if it has wrong parity, I thought about, yes, I make one more step. Sometimes you need two more steps, yes, because if the next step is even, it doesn't change the parity. So you need to wait until the next odd step actually. Do you have the same problems here? Okay, let's review again. Oh, you have binary. Okay, binary. Yes. Same mistake as me. Yeah. Okay, if you can run this 4, then you decide the rest. Okay, that's too much actually. So it would be enough to have one mistake. So having okay in compilation error also having 4 in compilation error runs test 1. That's also that's not good. So okay, okay, so you just okay, so let's read both of them actually. So here I believe you have the same mistake, right? What? Plus, no, you do something strange. No, you do something strange here. Here it is, okay. Okay, I don't know what was your idea here, but you doing something really strange here. That actually should work. Why doesn't it work? So if my sum is enough and the difference is even, it actually look okay. Why it doesn't work? Let's see. Can you see why I can? Well, okay, because you can't output 0. Okay, but you have example with 0. No. Yes. Okay, so you didn't test on examples. Okay. Not cool. Not cool. Okay, problem E. Oh, problem E is nice problem actually. So, okay, so we have this tree. Let's move to the picture. So this picture kind of explains a lot. So we scan the tree in some strange fashion. So we go left, right, left, right, left, right. Yeah. When there is nowhere to go, we go up. It's described very strange here actually. But if you look at this picture, you can see. So we go left, right, left. Yeah. When there is nowhere to go, we go back. Yes. Then we go here. Then we go here. Visit all this. Visit all this. Then we go here. Visit all these parts. And we need to find number of elements we visit until we have to the exit. So one of the leaves contains exit. We need to go to this exit. idea. So again, that you cannot just simulate it because number of elements is too high. So you have 2 power 50 elements. You can just count them. Yeah. So you need to do it fast. The idea is very simple actually. You don't need to count every single element. You can count them in blocks. Yeah. So you start from the root and go to the left child. Yeah. If your exit is in the left child, then you will not go to the right because you will not exit the left subtree until you visit everything in the left subtree. Yes. So if you go to the left subtree and here is your exit, you will not go here. That's observation. And if this exit is in the right subtree, then what will happen? You will visit everything here, everything. So whole this subtree will be visited. Only then you go back and go to the right subtree. Yeah. So you have the answer for now. We go recursively. Yes, we do the same for this subtree. Yeah. So for the subtree, we go to the one part. If this part contains exit, then we just go recursively there. If it doesn't contain exit, we visit everything in this subtree. No, we know how many elements in this. There's 2 power k minus 1 elements. Yeah, visit all of them, then go back, then go here, and again do recursively here. Okay, hope it's clear enough. Let's read my code. Code is really simple actually. Okay, my code is over. Okay, I believe it can be done even easier than this. So what I do recursive operation. Yeah, in my recursive operation, I give subtree as a segment of leaves. Yeah. So here I go. I have leaves from L to R, non-inclusive R. Yeah. And my exit in position n. N is position of the exit. Yeah? So I see if I am in the last row, it's actually like in a segment tree in some sense. Yeah. So if you visit the last row, then you are in the exit. Yeah. Invariant is that my segment contains the exit. I only do recursion if my segment contains the exit. Okay. So if I am in the last row, I just return. I finished. Yeah. If not, I visit my root, this root. I visit this root, increase the answer. Then I check where is my exit. So I find the middle. Check if the exit is in the left part. So if it is here. Okay, D is my current way. So okay. So D is where I need to go. So I go. Okay, I go 1 to the left and 0 to the right for some reason. I don't know. So if my exit is in the left part, yes, and I need to go to the right part first. Then I go to the right part, visit everything here. I have that many elements in the right subtree. Yeah. Then I go recursively to the left subtree. Yes. And so since I go to the left, my next move must be to the right. Yeah. So this direction is right. If my n is in the right part, here, then I do the same symmetrically. Yes. So I see if I need to visit left part, I visit whole left tree, and then recursively go to the right tree. Okay, clear enough. So that's it. I just recursively go through this tree and skip the entire block. So if I know I will visit the whole subtree, I will just add the size of the subtree to the result. It's actually pretty close to the logic of the segment tree if you think about it. Yes. So the trick is you have only one recursive call. So you traverse the tree. Normally you have two recursive calls. You go to one subtree and go to another subtree. But here you need only one recursive call because the first recursive call will just visit the whole subtree. You can just count how many elements and add it to the result. Yeah, you don't need to have this whole recursive call. No, that's basically, so that's the whole solution. Very nice problem, actually. If you didn't solve it, try to do it. Just write your own code. And again, Alexis, come on. Run down test 1 again. Come on. Come on. Test 9, that's interesting. Mm, how? How? Okay, so use long log, so it's not in the integer flow. Okay. But okay, this should be one LL. Okay, that's problem I know. That's something I did couple of times. Okay, this one should be one LL. Yes. If you do it like this, then 1 is 32-bit by default, and then you move it and you have integer flow. Thank you, C++, for my well spent time. Okay, so I believe that's the whole fix. Yes, that's the whole fix. Okay, at least you found it pretty fast. Yes. So how much time you spent? Okay, in 4 minutes you found it. Okay, okay, good for you. Any other mistakes? Time limit. Oh, okay, you have time limit. Interesting. Oh, that's overcomplicated code. It should. Nice. So we have this full cost function, which kind of returns the cost of this part. Yes, but this function works in linear time. Yes, because you have this. Because okay, so this function is slow. So instead of having this function, you just need to calculate like 2 power n minus 1 how many nodes you have. Nice mistake, actually. So you try to do this the right thing, but okay, but just uh so the function you needed actually is slow, but okay, I believe you fixed it. Yes, okay. Any questions by now? No? Okay, we've almost finished with the easy problems of this contest. Last problem is F. Okay, F is messy problem. I don't like it, but it is approachable at least. So what we have in problem F, so we need to find blocks, very strange blocks like this. You need to carefully read the problem statement and then implement exactly what's you needed here and do it carefully. Don't like this problem. But again, what we need to find? We need to find blocks like this. So I start looking for this block from the middle. So I find this, how do you call it? This okay. So this character, and then I move from this character left and right to find the character. So what I need to have to the left? I need to have some prefix of letters. I have A to Z, digits, and underscores, and then letter here. Let's put okay. Let's so let's have let's name so all letters are the same. So let's X is a letter, 1 is a digit, and underscores here. So I have some letters, digit, and underscores here, and then some letter here. Yeah. Then to the right, I have some non-empty. Okay, this part I missed. Of letters and numbers, some letters and numbers here. Then you must have dot, and then some letters. Hmm. So what I'm doing here, I try to find all possible strings before this character. How do you call it? How do you call this character? Actually, I don't know how do you call it. At. Okay. Why it's in Russian? Why my Google is in Russian? Not sure actually. My Wikipedia is in Russian. Very strange. At sign. Strange name. Okay. So you take this at sign and you find all possible strings before it and after it. Yeah. And I calculate number of them as X and Y. So X is number of strings I can put before it. Y is number of strings I can put after it. And I just multiply them and get total result. Yeah. So how you find this X? So you start from at sign. Then you move to the left. while you have some letter or digit or underscore. Then if you have a letter, then you have this string. And I just do it by brute force. Go left to right or right to left, and just extend until I have something which is not letter, not digit, and not underscore. Some, I don't know, question mark. Yeah. Okay, this is another dot. You have not question marks, yes. You have dot, or you make another add sign, yes, something strange. Then you stop. Yeah. And you just count how many letters you have. So from every letter, you may have a string like this. Then you do the same basically here. So you find the next element which is not a letter or digit. So it may be dot, it may be add sign, it may be underscore. If it is not dot, then you stop. Nothing interesting can happen in the right. If it is a dot, then you need to take all this part, you need to take the dot, and then you take some letters. And again, you do the same thing. You count how many letters you have here, and from every letter you may have any of these prefixes. Yeah. And you just count. So I have 4 prefixes here, some number of prefixes here, and you just multiply them and get the result. Don't like this problem. But again, it's technical, but you need to learn how to solve technical problems. It's pretty important skill actually. It helps not only to solve problems like this, but when you go to the highest level, when you have some strange algorithm plus technical stuff. Yes. So if you spend too much time on this technical stuff and don't know how to implement it, so it's easy to debug. You just can't solve the whole problem. So and okay, very many hard problems involve some technical stuff. So you try to just get these skills or just little by little. Yes. So this is not that difficult problem. It is not very pleasant, but not that difficult. Okay. So you can do it. Just try to solve it slowly and carefully. Check all the cases, and okay, that actually helps you a lot to solve harder problems later. Okay, let's read my prompt. So I have these few helper functions just to check it, because I need to check it a lot. And here, maybe you have these functions in C++. I don't know C++. So I scan my string and I find this add sign. Yeah. Now from this add sign, I go left and I go right. So I go left until I have something which is not digit, not letter, and not underscore. Yeah. Then I break. If I have letter, I increase the counter. Yeah. So that's a number of good prefixes, number of good strings before this add sign. Yeah. Then I find the closest character which is not letter or digit. Check if it is dot. If it is not dot, continue. Also, if I got this part in my first submit, if I have add sign and then dot, it's also not possible because this string must be non-empty. Okay, so you skip this. Now you have add sign, some non-empty string, dot. Then after this dot, again, you count how many letters you have. That's number of possible suffixes you may have. Yeah. So you count all these suffixes. And then you multiply number of possible prefixes, number of possible suffixes. That's your result. Again, not the worst possible problem, actually. I solved problems which are much more messy than this. Yeah. It's hard to get some pleasure out of solving these problems, but after you're doing it for a couple of times, it's not that awful. You just do it. Okay, I need to do this. Okay, I will implement some code, and you are programmers, for God's sake. You need to enjoy programming. Okay. Okay. So what mistakes you can have here? Let's find mistakes here. Oh, it's very very similar to my code. is alpha checks what I think it checks. Up, 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 up. Okay, but that's not dot. Okay, you doing left to right. Okay, I find it more convenient to go from this add sign in both directions because they kind of independent. You go left to right, eh, should work actually. So alpha checks if it is letter, right? Probably, yeah. So if I can continue, so I need to start from some letter. Okay, if it okay, so increase it. Okay, okay, okay. So len one is basically my x. Okay, if you reach the end or you reach the dot, you just stop and continue. Okay, stop from this point. Okay. Okay. Okay, you skip everything except add signs and dot. This includes underscores. Okay, okay. Not digital. What's it? Okay. Oh, I believe you have the same problem as me, no? No, 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 no. 13 or 26. No, not the same. Okay, let's find the test. Oh, okay, it's hard to. Okay, it's long test. So I actually need to read all this stuff. Okay. So if you reach the end, and if it's not dot, then you continue. If you reach the end, and if it's not letter, continue. Okay. Uh, Else you start from the next character. And what? And all the digits, or all the letters. Len 2 is this. Actually looks not bad. It looks okay. I don't know where's the problem. Okay, let's see what was the mistake. I'm curious. Okay. So you can't skip from this point. You need to skip. Okay. You can just move I to this position because you skip all these characters. Okay, but you can't use them in future. Okay, that's because you're going left to right, not from the middle. It's going from the middle much easier in this case. Okay. Okay, we're finally moving to the last two problems. It will be painful. Okay, okay, problem G. Problem H is fine. Problem G is painful. No, let's go. No, let's go. Okay, first thing you need to know about problem G, it is about game theory. Yeah, so it actually involves some grindy shenanigans. So let's see. So if you need to watch my lectures, so I will advertise myself. I will. So it's also in Russian. It's not my normal computer. It's just no. In this computer everything is in Russian. Okay. Pa-pum, pa-pum. Pa-pum, pa-pum. No. Somewhere here in first semester. Pop. Yeah. Here we have lecture about graph. Always make a move. Okay, don't talk. I'm talking. So if you know nothing about Grandi theory and graph games, just watch this lecture. I believe it's so we need only very simple part of this theory. So again, the idea is that if you have a game which can be split into two independent parts, we can combine these parts by calculating some magical number and sorting them. Yeah. Okay. Okay. Just pop, pop. What's happening? So you have this. Let's do it horizontally for simplicity. Yes, it's vertically for some reason in the problem, but let's do it horizontally. Pop, 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 pop. So if you put your what you do claim, okay, reclaim. Okay, so if you reclaim some element, yeah, so you basically make this element unused in future and these three elements unused in future. Yeah. Yeah. So basically, when you choose one element, you block this element and these three elements. Yeah. After that, so let's look at elements you can use in future to put your to reclaim your something. Yeah. Let's say put some tokens. Let's say you put a token and you're not allowed to put tokens here. Yeah? It looks more like game theory. Yes. So let's see. So I can put tokens here. So you have one part here, you can put tokens, and another part here. And these two parts are kind of independent. Yeah. So you can play some game here of putting these tokens, and you play some game here. Yeah. And these two games do not affect each other. Yeah. So basically, you have two independent games. And when you have a situation like this, you can use Grandi theory. Okay, so basically what you do, you choose your move, then you split your game into two independent games. You calculate some magical number here, let's say G1, yeah, and some magical number here, which is G2, yeah. Then magical part, the magical number for some of these two games actually equals to G1 XOR G2, and here use bitwise XOR. For magical reasons. It's not that important today. You can watch the lecture. I kind of prove it, but not that important. Yes. So you calculate some magical number here, XOR these two numbers. Then you have magical number of these positions. Now you try all possible moves and see all the magical numbers you can go. And now the magical number of your position is actually max of all possible. So my magical G is max of all possible XORs G1, XOR G2. And max is the minimal non-negative integer which is not in the set. Okay. I don't want to repeat the whole lecture. It's okay if you never saw it before. It's okay not to solve this problem, obviously. Yeah. So to solve this problem, you need to know all this theory and also implement a lot of code. I know. So again, this problem has difficulty 2100. Why? I don't know. Okay, maybe it was some special contest, and for special contests, okay, for special contests, difficulty sometimes calculated strangely. So maybe so okay, maybe that's because it. For special contests, difficulty sometimes is calculated not the same as for regular force contest. So maybe that's it. Sorry about that. Difficult problem. Okay. And now you just do now you just need to do basically dynamic programming. So your state is always some segment with some so you have some segment with removed element here, and you do dynamic programming. I implemented very so I don't want to show you my implementation actually. Okay, I will show you, but I don't like it. So my implementation is terrible actually. I rewrote it a couple of times, so it's not very long. It's less than 100 of lines, but so what I'm doing here, I basically do lazy dynamic programming because I was very tired at this point. I decided I will do a lazy programming. So I just give it a position. I give it a position and it calculates the grindy function, or it's called grindy function for this position. And here I do memorization, just normal old memorization. I believe I don't need all this stuff actually. Can we simplify it? I believe I can simplify it actually. So I have two different cases. When I have nothing in the segment, so when I have segment and nothing inside, then I do this stuff. And when I have something inside, when I have some blocked like this, then I split it into parts and calculate XOR of them. I believe I don't need this part actually. Let's optimize it actually. Let me. I believe we can do it just like this. Let's try. Boom. Again, I spent an hour solving this problem, so that's not the first version of this code. We have a contest right now, right? No chance. No chance. Okay, so I will show you the code which definitely works, and we will see later maybe if we can simplify it or not. So my code works like this. So let's take this. I hope this code works. Let's try it on examples at least. But these examples are kind of boring. Okay. -1. Okay, it doesn't work. Okay. Let's not spend more time here then. Okay, let me show you the code that actually works. I will not debug it in online. It will take too much time. So what I'm doing here, so if I have nothing in the middle, I check which move I can do. So again, I first I encode every row with number 0, 1, 2, 3. Yes, where 3 is both cells blocked. So like 2 bits. I need 2 bits to check if each cell is blocked or not. So I have number from 0 to 3. Yeah, depending of what. I also add 2 elements 3 in the on the side. So I always have, okay, just for simplicity, because so I can do this basically. Actually, I don't need this. Okay, so what I'm doing? So I scan my array and check if I can make the move. If I can make the move, I make this move. You see, so this I modify array A, so I block this element. It's incorrect. It should be equal 3. Why? Let me so I copied the wrong code. Yes, equal 3. Copy. It's also equal 3. Okay, doesn't matter. This I don't need. Okay. So I go left. I scan all my possible positions. Check if I can make this move. If I can make this move, I make this move, modify my array, and calculate the function, grandy function of this position. Yeah. So I basically try to make all possible moves and calculate grandy functions of all these positions. And calculate max of all these values. I could split it here actually. Doesn't matter. Doesn't matter. Okay. Strange code. Now, if I have some blocked values in the middle, so free means both cells are blocked. So if I have some blocked segments in the middle, I find these blocked segments. So I find segment between one blocks and to another, calculate this inside segment, and calculate for each of them, calculate grandy function and calculate XOR of all of them. Yes, I can simplify it. Okay, doesn't matter. I will not do it now. So I have one of two things. Okay. How my code works. Very strange. So you have a position. So if in the middle you have two blocked cells, you cannot go here, you cannot go here. Then I calculate grandy function here, calculate XOR. If I don't have this, then I make one move. So I check which cell is not blocked, make this move, block these 4 cells, and then calculate grandy function of the result. Yeah, and then calculate max of all possible moves here. Terrible code, terrible code. Okay, it was a difficult problem, yes. So it's okay that nobody solved it. Did you try to solve it? Okay, it doesn't look like a solution, intended solution. I mean, no. You need all this grandy theory here, unfortunately. But okay, that's problem G. Over difficult, I agree. It's not supposed to solve it during the contest. But again, try to solve it after the contest. It is difficult, but it's solvable. If learn grandy theory, solve some problem about grandy theory, and then try to approach this problem. So when you know grandy theory, it's just implementational problem. It's difficult, but it's doable. Okay, finally, problem H, last one. For me, it was actually easier than problem G, like I told you, yes. But okay, still nobody solved it. Maybe because you stuck on problem G as well, yeah. So problem H, what you need to do? You need to find, let me tell you. So what we have here? So we have some long string S, and we have some pairs of short strings. It's important they are short, actually. So we have some short string A and some short string B. Very short. Yeah? Very short. And we need to find the smallest string which contains both A and B. Yeah. No, basically, how the string can contain A and B? No, it should contain one of them in the left, one of them in the right, something like this, right? Yeah. If they're in the middle, you can make string shorter. Yeah. If you can't make it shorter, then you do something like this. So basically, what you need to do, you need to find the position of string A and position of string B, which are very close to each other. Yeah. So let's find all positions of string A. So imagine you have multiple positions of string A. Okay, let's make it really short. So it's okay, let's like this. So I have positions of string A. And you have some positions of string B. Let's have some small. Yeah. You need to find closest A and B. So we have this closest, or maybe this is closest, or maybe this is closest. So you need to find closest positions of string A and string B. Yeah. That's it. That's the whole problem. So how you do it? How you do it? Again, if you think about it, what you can do, if I have these two sequences, you have sequence of position of A, sequence of positions of B. You can do kind of two pointers method, like merge into sorted arrays, and find two closest elements. Yeah. Yeah. But it will be slow. Yes. Okay. So it will be slow if I have many positions here. So if both strings have many positions, I have many positions here, many positions here, then it will take a long time. Yeah. What you can do, how you can speed up. So let's see, if I have many positions of string A, but small number of positions of string B. Yeah. So if I have many, so if string A occurs many times and string B occurs small number of times, what you can do, you can actually iterate all occurrences of this string B only. And for each occurrence, you find the closest position of string A. So you find these two occurrences here, these two occurrences here, these two occurrences here, this occurrence here. Yeah. So for each occurrence of string B, you find closest occurrences of string A using some binary search. Yeah. If you do it this way, then you will have time complexity based on the smallest list. You see? Sometimes it speeds up the solution. Okay, that's like nice observation that you may have if you solved a couple of times like this. Then if you, so you answer the question, you answer the, okay, so yeah. Sorry, I can get your question. So can you repeat again? Hello? Can you repeat the question? Sorry. Okay. Okay. Not sure. Okay. Okay. If you can do it again, I would answer your question, but I just couldn't hear. Sorry. So, you have we have chat. We have chat. Nice. Um, what? What? Wait. What? Not okay. So how much is H rated? Okay. This question. Okay. I'm not sure. Something about 2000 something to 500 maybe. Okay, which one? This one. Yeah, that's it. 2500. Again, so again, so let's say that string A occurs number of n, so n of A is number bare of occurrences. Okay, it's a difficult word. Substrings equal A. Yeah. So what is the idea here? Idea here to solve problem not in NA plus NB. That's too slow. Yeah, because I will give you a lot of queries. Each query will have linear number of occurrences. Yeah. The idea is to solve it in minimum of N of NA and NB. No, multiplied by log, doesn't matter. You can do it without logarithm, but I just did with logarithm with binary search. You can do it with binary search, but that doesn't matter. Why can it be better to do it like this and like this? No, because of the reason. So if you look at sum of all occurrences, so sum of all n of a for all for all strings, total number of all strings is linear. Yes, because I have at most 4 characters, so it is not greater than like 4n. So it's linear. So if you have total size is linear, it's hard to get a lot of pairs such that both elements are linear. Yeah, like okay, imagine. So if you have one slow request, then you have this position. So if n at a should be about n, yeah, and n of b should be about n, yeah. It shouldn't happen very often because the total size is linear, yeah. So if you have a lot of slow pairs, they cannot be very slow. Yeah. Yeah. Again, and if you think about it, when it's this balance actually about square root. Yeah. So you may have like square root of n elements. Each size will have square root of n. Yeah. So from square root of elements, you will have like n pairs. Yeah. And for each pair, the size will be square root of n. And that's like the balance of between size and number of string. Yeah. So like in worst case, you will have n log n solution. And square root of n solution. By log n at least, because I use binary search. So it is some type of square root decomposition actually. But I don't introduce square root. So sometimes when you have square root decomposition, you do it explicitly. So you can do it here also actually. You can do it like this. So you can split all elements into small and large. Yeah. So you split all strings in some strings which are less than square root of n, and elements when n are greater than square root of n. And here we have no more than n such strings. Yeah. So you can solve this part separately, solve this part separately, solve so depending on so if you have small and small string, you can do it just brute force. If you have small and large, you take small string and do binary search. If you have large and large, then you do two pointers method, but you can do it at most n times. Something like this. Yeah. So you can do classical square root of n decomposition. Yeah. But that's actually more convenient way to do it. Yeah. So instead of just explicitly introducing square root of n, splitting it into parts, sometimes you can do it like this. So you just go small to large and just make sure that number in the worst case, this sum of all small elements will be not greater than square root of n. Okay. Hope it was clear enough. Code is really simple. So look at comparing to problem G. So here I calculate all the positions. So I calculate just positions for all possible strings of size at least at most 4. Yeah. Here I do memorization. So if I have the same pair multiple times, I don't know, is it possible or not? I don't want to deal with this. So if they give me the same pair multiple times, I just memorize the result. Okay, here I swap them. So A is a string which occurs less number of times. Yeah. And okay, so this is the whole code. So what I'm doing here, I go, yeah, I iterate over all positions of string A, which occurs less number of times. Find using binary search closest position in array B. Yeah, and check two positions, closest to the right and closest to the left. Yeah. In both cases, I know the kind of the borders of each string, so I find the smallest substring which contains both of them. Yeah, that's it. That's the whole interesting code. So interesting part happens here actually. Everything else is just technical parts, just finding finding all positions, some memorization here, and that's it. Yeah. So that's the only interesting part actually happening here. Again, the idea is if you if you look at pairs between two arrays, you take the small array, yes, and look at only closest elements in the large array. And that way you have small time complexity. Okay, let's see. This was problem G. Did it still in the queue? Okay, it will fail also. Okay, I will probably. Okay, I will try to write beta solution for problem G and probably post it later. Any more questions? No. Difficult contest, difficult. I try to make contest not that difficult, and I almost succeeded up to problem F. I believe these problems are okay. That was too much. That was too much. Okay, it's not me. It's just Codeforce's difficulty system doesn't work. Okay, just assigning difficulty to just 2100 to this problem is strange. Okay, if you don't have any more questions, then see you next week.